My name is Ivica, and as he said, I will be talking about defining an abstract architecture for managing unstructured data using MongoDB, and I will showcase our main product, which is the vDrive. Before I begin, last time I presented the paper, I started off with a joke, and it was either a tough crowd or a bad joke, but I won't be trying that again. On the other hand, since gamification is all the buzzword these days, throughout my presentation I have hidden 3 puns or jokes or references, or whatever you want to call them, and whoever guesses those puns will have a chance to win this awesome cupcake. It says, I believe it is awesome, really. Okay, this is the outline of my paper, of my presentation. I will start off by explaining what digital libraries are and how they influenced this paper. Next, I will be talking about data in this context while handling digital data. The main portion of this presentation will be talk about MongoDB, which all of you heard of. The next part, I will talk a little bit about the vDrive, maybe some testing and conclusion in the end. Okay, so let me begin. I believe that we can all agree that knowledge access and knowledge sharing is a really important part of contemporary classrooms and modern institutions, teaching institutions. Considering the importance of knowledge sharing and knowledge access among students, it is important that a system, information system which handles this is well built, that it is highly available and a scalable system. Also, we can all agree that every information system should have a disaster recovery scenario. In the past years, more than a few digital libraries lost content due to floods in India. There was a tornado in Texas and a few earthquakes in Indonesia. So all 3 of those university libraries lost content because they didn't implement a disaster recovery scenario. When we talk about digital libraries, we assume that they handle digital content, and a basic disaster recovery scenario for huge amounts of digital content is to simply copy the data on a distant location, which is on another tectonic plate or 300 kilometers away, and so on and so on. There are currently 2 or maybe more approaches that handle digital content. First, both of them have their flaws. Those approaches are either using relational databases or using file system-based repositories. And both of them, as I've said, both of them have major flaws. These flaws may not be visible from the start. You start using the system and it's working great. And then you need to add another server. Your current architecture doesn't support any more data. So you either add another server or you add more hardware power. So you basically vertically scale the system. You go out and buy a more expensive processor. You buy more HDDs. But the bottom line is that you can add only so much power to an existing server. These are the cons of the current approaches. First of all, it's really expensive, and you know how economy is these days, so no money for the IT whatsoever. If you decide not to scale up your system, there is only a finite amount of data which you can store in your architecture. And what happens when the usage patterns change, or if the server load changes? Does that mean that your hardware is underutilized? So you wasted money, basically. When I say data, I mean 2 types of data, basically structured and unstructured data. Structured data is basically all the data that you can fit in a table or in a table-like structure, basically what you can see on this example. On the other hand, there is unstructured data, which is basically everything else. all the PDF files, all the emails, all text files, all movies, that's all unstructured data. And there was a recent study in 2012, I believe, which shown that more than 80% of all the data in small and medium enterprises is actually unstructured with a tendency to grow. So there is a real need for a system that handles unstructured data efficiently. Okay, while we were researching some cool stuff, we stumbled upon MongoDB. MongoDB is a NoSQL high-performing distributed database, which it was built in 2007 by 10gen. It is a document-oriented database, which means that the data is saved inside of BSON documents. BSON is basically binary encoded JSON, so it's human readable, but it's also binary data. MongoDB is, of course, free and open source software. They have very nice documentation on their official website. There are also free online courses, and so on and so on. I don't want to be a marketing guy. Next to all that free stuff, there are also drivers for main programming languages, namely C, C++, C#, Java, Node.js, PHP, Python, of course, Ruby, and so on. There is a support for more languages. This slide shows a little comparison of relational databases and MongoDB. In this example, on the left-hand side, we have data that is written into rows. These rows are organized into tables. Tables are grouped into databases, and each table has a primary key. In addition to that, tables have relations between them using the foreign keys. On the other hand, MongoDB stores data inside of documents. That's how they call them. Documents are grouped into collections, and this is the first difference between SQL and MongoDB. When you have a SQL table, the data inside that table is highly structured. So the structure is imposed on the data. Every field has to be there. Every field has to be present. On the other hand, MongoDB does not impose structure on documents. So each document inside of a collection can be different. Basically can be different. It's logically sound to group similar documents, but they don't have to be exactly the same. They don't have to have same fields. As in the SQL world, collections are grouped into databases. There is some implementation of a primary key, which is the underscore ID field. And because there are no relations between collections inside of a single database, there are a few ways to model your data, and one of those ways is to use nested documents. So basically, a document inside of another document is similar to foreign key relations in SQL world. This is a simple example of a document which, by the way, describes me. Wow. As you can see from the top to bottom, there is a underscore ID field, which is the primary key, and the data type of that field is a special data type called object ID. It's a MongoDB defined data type. And as I've said, from top to bottom, there are various data types such as strings, integers, arrays, date, time, and there is a nested document company which is inside of a parent document. There are three main features for which we chose MongoDB, and the first one of them is replication, which I'll explain in a couple of minutes. Replication, as you may know, is basically copying the data to multiple locations. It's a automatic method, and it brings redundancy and high availability to your cluster. There are a few roles inside of replica set, and the first and foremost role is the primary server. So it's marked with a P. The primary server is responsible for all the write operations that the cluster receives. So each write operation goes to the primary, and secondary servers marked with an S replicate that data automatically from the primary. There is also a built-in mechanism called the heartbeat, which is basically like a ping, and it is triggered every 2 seconds. So each server in the cluster basically pings all the other servers to determine if they are up and running, if they are alive. So in a situation where a primary server goes down, what happens? Does that mean that your cluster is unavailable to receive new data? Well, yeah. But there is a slight delay, maybe 10 or 15 seconds. I will demonstrate it a little bit later. So there is a delay because the other secondary servers will figure out that the primary is down, and they will hold an election process. Basically, each server has one vote, and they cast their vote for a new primary. And then a new primary is elected, and the cluster just goes on performing like it did 10 seconds before. Replication is also a perfect setup for disaster recovery, because you may decide to move one of your secondary servers to another location, to another building, another city, another country. It doesn't matter. It's all done online. In addition to that, there's more. In addition to that, those secondary servers may be configured so that the data can be read from them, basically lightening the load on the primary server, and thus creating a redundant, highly available cluster. When I say high availability, it's only fair for me to explain how would you plan high availability using MongoDB. As I've said, there is an election process which is held each time a primary server goes down. Majority is a really important concept when we talk about replication, because majority. Let me explain majority. It's really simple. Majority is basically half of the configured set plus one server. So if you have 3 servers, majority is 2, as suggested in this table. Why is majority so important? It is really important because your primary server can stay primary as long as it maintains majority. So if the primary can contact more than half of the set, it will remain a primary. Another important internal mechanics of replication is the priority, and priority is a user-defined preference, or simply a number between 0 and 100, and it shows your preference towards a particular server because of its I don't know, hardware or its network connectivity and so on. Basically, every server that has a higher priority will most likely become the primary. Not most likely, will definitely become the primary. Let's plan a little high available cluster. Let's do the math real quick. Let's say that you want to plan a cluster that can handle 2 servers, two offline servers. Basically, it's all about majority. So you need a 5-server cluster, because if you lose 1, then you lose 2 servers. You still have 3 servers available. You still have majority. So the whole replica set, the whole cluster will continue to function even though 2 servers are offline for any reason. And if you replace those servers, nothing will change. Everything will continue on working as if nothing happened. One major danger that people just seem to or forget or I don't know what, they all assume that replication is a backup solution. Replication is not a backup solution. It is not. What happens when someone runs a query that removes everything from the database? Well, yeah, secondary servers will replicate that query and everything is deleted. It's not a backup solution. So proper backup procedures are important even though. Okay, I have planned a little demonstration, sorry, to show you how replication works. There are 3 virtual machines set up on my laptop. Just real quick. Oh, okay. Terminal console, yeah. Okay, as I've said, we have 3 servers, and as you may see from top to bottom, this line that says secondary, and the primary. It is what it is. So there are 3 servers. One of them is primary, and there are 2 secondary servers. I will now query this database. These are the collections that I talked about. Some of them are system collections, some of them are user created. And let's just okay, we have 0 chunks. So the database is empty. There is only a collection because I did a couple of writes to the database. I will now run a custom Python service, and I will upload a file to this database. Let it be a 20 megabyte file. We don't care. So while it's uploading, and here it is. The upload is finished, and as you can see, this is the IP address of the primary server. Okay. I will now query the database once more. Here is the file. So it's uploaded. As you can see, there are a few informations about the file, such as file name, its length, or the size, and the hash. Okay. I will now move to another server, which is a secondary server. As you can see, it says secondary. I will now just do some magic. Sorry. Okay. Everything should work. I don't believe it. Something went wrong. Sorry. This wasn't planned to go like this. We actually have our servers back at my school, but the VPN server went down. It's broke, so I can't use that. And these virtual machines are not so great. I don't know why. Everything worked yesterday. You know that. It's always like that. Nah. This is what I wanted. So I have now queried, after all these tries, I have now queried one of the secondary servers, and as you can see, there is a file which wasn't there a moment ago. So the file replicated from the primary server successfully. It's replicated to all the secondary servers. Okay, I will now shut down this this primary server to see what happens with the cluster. Okay, the server is now shut down, and if I check the status of my cluster, you can see that it's currently not reachable. So the primary server is currently not reachable. I will now try to re-upload the file. And it works. But if you noticed, this line here changed. So what happened here? There was an election while I was talking. The election process kicked on, and the cluster chose a new primary server, which now takes the role of writing the data to the whole cluster. So nothing really changed for the end user, only sweaty forehead, but nothing actually really changed. Everything works. It just works. It's magic of MongoDB. Okay, let me continue. I won't start from the beginning. Okay, another great feature of MongoDB is a sharding, and sharding is a method for storing data across multiple servers, across multiple machines. It basically splits the data to a few shards. This mechanism, this sharding is very useful for load balancing and also scaling. But when I say scaling, I mean horizontally scaling your whole cluster. It basically means that when you run out of storage, or if you run out of processing power for the sheer amount of data, you can just add another server. You just put another shard, configure it real quick, like I just did, yeah. And it will. There is a background process which will transfer a certain amount of data from existing shards to the new shard, thus balancing the load on all servers. MongoDB is not the first database to support sharding, of course, but MongoDB does it a little bit different. What they did is next. They added additional servers. So this is a schema of a sharded cluster. What they did, they added routing servers, and their role is, as their name suggests, they route queries from the client application to the appropriate shard or shards, because the data can be split among multiple shards. There are also config servers on the left here, as you can see, and those config servers store the whole configuration of the whole cluster in their own database, and they are responsible. They are responsible to know where each chunk of the data is. So the client application only queries the routing servers. It does not need to know how many shards is there. It's completely oblivious. It only queries the routing servers, and the routing servers then go out and split the query to two additional shards as needed. It's also important to say and to know that these shards are a replicated environment, so each shard is a replica set. The third feature that I really personally like is a gridfs, and it is a specification for storing files which are larger than 16 megabytes. Basically, BSAN documents can store 16 megabytes of data, but if you need a bigger file, if you need to store bigger file, there comes the gridfs. Gridfs can be considered a database file system. It works by splitting the file in 256 kilobyte chunks, and those chunks are written in a special collection which is called chunks, FS chunks. There is also a special collection called files, which I queried in my demonstration. And that collection holds all the metadata about a file, such as file name, file size, upload date, and so on and so on. MongoDB is actually like a skeleton to our research, to our product, and gridfs is basically the spinal column of that skeleton. It's also important to know and to say that MongoDB streams. It does streaming both when you store the files and when you read the files also. So it's a streaming environment, and it also bypasses file system and operating system limitations on file size. You can basically store any file size as long as you have a proper hardware, of course. And a short while ago, in a school not so far away from here, one of my colleague, my dear colleague and co-author of this paper, Milorad, from the audience, he came up with an idea. We have a information system in our school which is like a one-way communication channel between teachers and students. Teachers use it to grade their assignments and papers and to input grades. And students on the other side log onto the system and they just read out their grades, and that's all they can do, basically. Not everything, but basically the main part. So he came up with an idea to extend that information system with a hardware-software plugin, basically, that handles unstructured data. And we figured to use it for the students to upload their assignments, to upload their files on our own school servers. Each one of them should get 1 gigabyte of space. Basically, a cloud within our school. It was supposed to work that way, and it will work that way. While we were developing that solution called the V-Drive, we stumbled upon an idea to create a abstract architecture that will be an addition to every information system, extending it with unstructured data handling capabilities. Basically, you buy 2 or 3 used servers, you install our product, and there you go. Your information system should be extended and expanded with unstructured data handling capabilities. The first and foremost condition was that this system should be very low cost or completely free for the user, and it should also possess a uniform communication interface, so it could interface with almost any existing information system. So these are the conditions that we figured we should fulfill. And on the left-hand side, you can see the condition, and on the right-hand side is the solution to that condition. So we built a RESTful web API, which uses JSON as the communication format. In order for the system to be with minimal expenses or possibly free, we of course used open source technologies. And for end users' ease of use and setup, we automated the hell out of it and put a web interface. Everything is simpler on the web, so they say. This is a outline of the proposed architecture, and it consists of base system, database layer, and a service layer which communicates with the DB layer. For the base system, as you may have noticed, we used custom CentOS minimal distribution, which comes with all the batteries included. MongoDB is installed automatically. Your hard drive is partitioned automatically. I will show you that in a little while. All the custom services that we built are built in, and everything is up and running in no time. We built that distribution to provide a uniform experience for administrators and users. Someday in the near future, when this system becomes popular, I hope so, you could just say, oh, I'm using that custom CentOS, and every administrator will know, yeah, those services are running and these ports are open and everything is working. And it's also plug and play with look, no hands. The installation is completely automated. We've used a CentOS's feature of kickstarting, which is basically a predefined set of answers to those basic questions. What will be your password? What's the partitioning scheme, and so on. And this is the proposed partitioning scheme. As you can see, there is a boot partition, a root partition, and a var partition. which is the largest one, and it will grow to the maximum size of the hard drive because MongoDB uses var partition as its repository. It stores data on the var partition. For the web API, we used Python, of course, big heart for Python, and its Tornado framework. Because Python is built into every Linux distribution, it's very easy to read and to understand and to use, and it also comes with lots of good features. To boost it up, to put some steroids in it, we used the Tornado framework, which is a asynchronous, data-driven, I don't know the words that they describe the Tornado in. It's basically a very nice piece of software. It's really fast. It's faster than Node.js, all of you. It is faster than Node.js. Yeah. And to conform to a RESTful architecture, we used basic HTTP methods such as post, put, delete, and get. And this is a example how would a client application, whatever it is, how it would create another user. Basically, it would make a post request as written and provide basic data about the user, and that's it. A nice response is also returned from the API. As I've said, and if you recall, MongoDB does not impose structure on its documents. So each document can be different. And it's really nice if you have a web scraping robot or something, or a logging application, something like that. But when you are building a business application, you want it to behave just as you envision it. You want to put some rules into it, and you want to impose those rules as much as you can. So we decided to use this Mongo Engine library, which is a Mongo driver on steroids, basically, and it provides, it's a Python library, of course, and it provides the user with a ability to define documents using Python. As you can see, these are two documents that I've defined, and it's the same document that I showed you an example of. So it's a user document with a company embedded into it, and it's really real simple Python code. There's not much to it. That's it. For the hardware part of this whole architecture, we used two Fujitsu RX300 servers, which we had just laying around, making noise, with those specifications as written. And we basically used each one of them as a separate data center. So we quote unquote created two data centers. Each of those data centers had VMware virtualization technologies on it. And we created a sharded environment in order to test this whole approach and this talk, this whole research. It's also, the picture is color coded, so it's easier to understand. We basically created a two shard cluster. Each shard had a 3 servers. And on the first data center, we put 2 servers, so one primary, one secondary. And on the other server, we put the second secondary of first shard. Confusing? No, it's not. And we switched places with another data center. So the second data center held another shard, which was also a replica set, and those additional servers that sharding environment requires. And in order to test this whole approach that we devised, we basically thought about it, and the file sizes that we use should correspond to expected file sizes that our students will upload. So there were 5, 25, 50, and 100 megabyte files. And for the first round of testing, we copied those files manually over the local network and over the internet. And those results are in red, and those results are orange. So manual copying is orange. Then we created a replicated cluster and uploaded the same files, the same file sizes. and we measured times. So those times are represented in blue. And as you can see, there is not much difference. So MongoDB does not bring, doesn't add any, I forgot the word. So there's no additional time when you copy the file manually. There's no overhead. That's the word. There's no overhead when you use MongoDB's replication mechanisms. It's just as fast as copying the file manually. We also tested this solution over slow links. So we used a VPN which was limited to 2 megabits per second. It was really slow and awful, but it just works. Everything works. No matter that the speed was very slow, it worked. And same as before, there was no significant difference between manual copying and Mongo's integrated replication mechanism. So, to conclude, there is a great need for systems that handle unstructured data as shown in the introduction slides. The solution that we provide using MongoDB and GridFS is efficient and is scalable to gigantic proportions. Actually, there is no data size limit that you can hold in a sharded environment, so no data size limit. And also, there is a disaster recovery scenario, which is a bonus feature that comes for free. And I will now thank you for your time. I'll just rehydrate myself and you think about questions. Yes? Yeah? Yeah? The election, there is maybe I forgot to mention, there is a built-in mechanism called the heartbeat. And that heartbeat mechanism is basically like a ping. It pings every 2 seconds, every server pings all the other servers. And if the pinging server, the one that sent out the ping, doesn't receive a response in 10 seconds, that server is considered to be down for any reason. Maybe it's not down, maybe the network connection broke, but there is no connection between them and it's considered to be down. So yeah?
If you have a cluster free,
yeah? Yeah, the majority is 2.
Yeah, but you have to leave 2 servers.
Yes.
None of which has majority.
Both of them propose themselves to become the primary, and there is maybe some simple math, maybe some complex math that determines which one will become the primary. The stuff that I know is that a server can become a primary only if it has the latest data written. There is a last write time actually in the logs. And the one that has the latest written data or has the highest priority will become the primary. If all the servers have the same priority, one of them will become the primary. It doesn't matter. One with the latest data, yeah, yeah. If they both have the same data, then it really doesn't matter which one. Yes?
I have a question regarding replication. At what point does it happen on the other servers?
It happens at every 100 milliseconds. So it's almost automatic. Yeah, sorry.
Does that mean that all the servers hold all the data?
Yes, they hold the same data set. It's not like sharding where the data is split, but the same data set is held on every server. I forgot to mention, there is a user configurable delay for replication. So you can configure one server to be delayed, let's say 4 hours. So that server will be late 4 hours to replicate the data, always. Yes?
You mentioned that replication and sharding is in no way replacing
For a backup.
So
Yeah.
what kind of backup solution have you implemented?
Yeah, we did not implement because we had no, we're guilty, but we had no hardware to support that. We only had 2 servers.
Okay, but if you had,
Yeah, there are,
using, considering
that you, Yes.
What kind of solution?
There are built-in tools to back up your single server or the whole cluster. It comes built-in with MongoDB. It's Mongo Export and Mongo Import. Those two tools. Yes, yes. There's something to dump. Sorry, to dump the data. Those backing up to automate, well, cron jobs. Why not? Why not? Any? Yes.
So if I understood correctly, you always keep the primary server.
Yeah, with the write operations, yes. Read operations. Oh, let me show you the schema. So all the write operations will target the primary server, and the way that your client application knows which one is the primary, basically when you build an application, there is a connection string. If you ever use databases, there's always a connection string which you use to connect, and you basically put all the servers in the connection string. So it's string this big, and the driver itself will know which server is the primary, and it will also know if that server is down. And
So the read can come from the secondary server.
yes, if you configure it that way. There's always a inconsistency between the data on the primary server.
My question.
Yeah, there always is an inconsistency. It's a trade-off. You choose to have a highly available cluster, but your data will not always be consistent. If you upload large files to the primary server, and those files didn't have enough time to replicate on the secondary will not have those files. It's as simple as that.
My second question is, how would you compare it with, for example, Apache Hadoop distributed file system?
Yeah, I'm not very much versed with Hadoop. I've never used it. The things that I've read is Hadoop is like it has a bunch of tools, and each tool is for a certain role. MongoDB comes with all that built in, so everything is out of the box. I'm sure that my answer is not an answer to your question. So I really don't know.
Quite similar, actually.
Yeah?
The replication and the rollback of the data and quite a lot of interesting stuff. So I just
Yeah?
thought maybe
No, I've never used it, no. We actually use the MongoDB because it has a Elasticsearch capabilities with a plugin. Actually, we needed that. And also it supports large files. Maybe Hadoop also supports them. We don't know. We didn't use it. Yes?
And if all servers have all data, then
Yeah.
if we have a lot of data, we really need a lot of powerful machines.
They don't need to be exactly powerful. MongoDB runs on, as they say, commodity hardware. We basically used, for our testing, we used machines that were more than 10 years old. They were Celeron machines with 512 megabytes of RAM and 20 gigabyte hard drives. And it just worked. Maybe it wouldn't work if the amount of data was too big, but you don't need all that powerful servers. Those can be used and actually commodity hardware. It's commodity. Any more questions? Okay, I thank you again for your time. Oh, thank you. What about the cupcake? What about the cupcake?
There are multiple steps. It's like, whoa, is that a joke or is it for real?
Everything is a joke and for real. So, did any of you catch any puns, any fun stuff inside of my presentation? Yeah?
There was a school, in a school not so far away.
That's one of them. So that's one. You have two more. It wasn't a reference to anything. Okay, but I'll give you one, so you have one also. Yeah?
Hobbies, cats.
Yeah, yeah, but it's real. I really like cats. No, maybe I did it too hard. So you have one. It's a Star Trek reference, of course. There were also two references, so I'll get the cupcake. Sorry. There was a... no, I closed it. There was a reference to a Unix epoch, the start of Unix time. In the table, 1970. Yeah, that's the second reference. And that is, what's that? That's the end of a Unix epoch. Nice one, Csaba. You win the cupcake. Yeah! Yeah! Nice one. There you go.